Hi, in this video, we're going to look at confounding variables in experimental design. All right, so a confounding variable, or also called a lurking variable, is a variable that correlates with our target variable and the predictor variable. And so what can happen is that the effects that we see, the relationship between the predictor variable and the target variable, could be stronger than they really are or weaker than they really are when we're not aware of the confounding variable. So what we want to do here in the video is talk about what are confounding variables and what can we do to protect ourselves from them. Now, we're not going to do very many actual statistical computations because this is more of just like an awareness aspect. And we're going to pull in some stuff from previous videos that we've taken a look at. All right, so a confounding variable is an extraneous variable that correlates with both a dependent variable and an independent variable. And the presence of a confounder can cause the experimenter to mistakenly attribute the outcome to the independent variable or not attribute it to the independent variable, depending on the relationship with the confounding variable. Confounding is a critical issue in experimental design that occurs when the effects of two or more variables cannot be separated, leading to an incorrect interpretation of the relationship between the independent variable and the variable of interest. All right, so let's run through an example. So here we're going to do, we're going to create, some dummy data to kind of just show the mathematical relationship of a confounding variable. So let's say that we're in the situation that exercise is influenced by our diet. So maybe true, maybe not, just run with it for this example. And we're a researcher and we're interested in studying the influence of exercise on weight loss. Now, weight loss will be influenced by diet also. All right, so here in this fake data mathematical situation, we have diet is going on, and we're taking the point of view for this example that exercise is influenced by diet, plus some other aspects that are not accounted for in this particular model. And so for this situation, weight loss is going to be a combination of exercise and diet plus an error term. Okay. And so when we look at this, this shows us that weight loss is going to be correlated with exercise and diet, and exercise is correlated with diet also. All right, so diet is a lurking variable, a confounding variable for this. Now, if I'm a researcher and I'm unaware of the importance of diet in this situation, I'll be focused on exercise and lose sight of what I should be looking at, the diet aspect. And so let's go ahead and run a plot. And so here, if I go ahead and visualize this, this looks like a really good model right off the bat. Like I'm feeling good about modeling weight loss based off of exercise with a linear regression. Now we know from how I built up the data that exercise is not sufficient to get the full story. And so if we were to run with the results that we're looking at right now, we will be missing a big chunk of the story. Now, unfortunately, when we're doing experimental designs, we don't really know if there's a confounding variable, a lurking variable, like hidden in the system that we're not aware of. What we're going to do, we're basically going to follow best practices to protect ourselves from the situation, but we never really know if we are, like how much at risk we're at. Is there a confounding variable in the system? All right, so let's talk about ways to protect ourselves from confounding variables. The first one, the most important one, is subject matter knowledge. So if I just know a lot about what I'm working with and I understand what's up, I'm going to be able to identify confounding variables in the system that I wouldn't be able to spot if I didn't have subject matter knowledge. Now, if I don't have subject matter knowledge, or if I do, it's a good idea to have an expert review my design before I go and start collecting data. A second pair of eyes might spot something that I missed. Now, after subject matter knowledge, the most important aspect to protecting ourselves from confounding variables is random assignment. Random assignment, what we're hoping that will happen is that by shuffling, if we randomly assign, measurements to different situations, that we can protect ourselves by just blocking and kind of like by having things just randomly dispersed. Now, random assignment doesn't really kick in too often, unless we get lucky, on small data sets. And so what we want random assignment along with a large sample size. So if I have a large sample size and I have random assignment, then by just dispersing all of the data points across all the possible combinations, what will end up happening is that if there's a confounding variable, its influence can be like separated from what we're looking at. Now, stratification and blocking on potential confounding variables is important. So stratification, what I mean by that is making sure that in my sampling, if it's possible that smoking is important on there, an important variable in what's going on, I want to make sure that I have smokers and non-smokers in my study. All right. Now, blocking, what I'm going to do, I'm going to make sure that smokers and non-smokers are receiving every level of treatment. And so the stratification makes sure that I have included the different levels of the confounding variable. The blocking is I'm going to distribute the potential confounding variables across treatment groups. Next one that helps protect us is replication at multiple times and distinct environments. So basically, I'm just changing things up. Let's say that I'm working with, let's say, imagine I have like an oven, and my oven doesn't actually reach the temperature that says on the settings. And I keep on using that oven for experiments. Well, there's a problem with what I have. Now, if I go to a different kitchen on the other side of the country, and I start doing things at different times of day, then that oven aspect probably won't come to bear as a confounding variable on the situation. Now, we can also do case control and cohort studies. So in case control studies, we start with the outcome, like the disease, and then look back at individuals who have the disease and who do not to see what factors may be associated with the outcomes. Cohort studies follow a group of individuals over time to see who develops the outcome and who does not, and assess various factors that may be associated with the outcome. Now, double blinding, what we do is we set it up so that in the treatment aspects, the things that we have control over, the people who are interacting with the subjects don't actually know what the treatment is for that subject. And so we set it up so that there can't be any biases, coming to bear, because the people who are involved don't know what they're actually implementing. And another thing that we can do is that, if I can collect data on additional covariates, I can include those in my multivariate analysis and just see that, hey, is there something going on? So let's say that age is correlated with a confounding variable. Now, what could help my statistical analysis? I have a confounding variable that I don't know about, but age is correlated with it. By including age in my analysis, the age can actually, in my multivariate analysis, can pick up that confounding aspect, and that can help lead me to figure out like what's going on the confounding variable as I reason through what's happening. Ideally, we would actually identify the confounding variable itself. So like here in this linear model, we include diet, which is the model that we would want to use based off of what we had. But frequently, we don't actually know what the confounding variable is because it's a lurking variable. If we do know what it is, of course, we're going to work with it and collect it and do our best to handle that. All right, I've got some homework problems for you to work on. The one that's most interesting is I want you to go out and find a data set with 3 variables that are highly correlated with each other. And what I want you to do is I want you to pick one to be the target variable, pick two to be predictor variables, treat one of those as a lurking variable. And what I want you to do, I want you to take the target variable, the non-lurking predictor, build a linear regression model. And then I want you to build the best regression model you can with the two predictors and the target variable. So you might want to do, interactions. You might want to play around with it, do different model structures, whatever you think is best. Use AIC to determine the best model, and just submit that. And so here's some code using empty cars, just to give you an example of what I'm talking about, where we have miles per gallon, displacement, and horsepower all correlated with each other. All right, well, that's all I've got for you. Life is short. Do math.